Have you ever seen a tornado? They are terrifying spinning columns of wind. Now imagine that tornado over an ocean. Imagine it growing larger and more powerful. That's a hurricane, a storm of incredible force and fury. Hurricanes are more than just big storms. They are forces of nature that can devastate coastlines and leave a trail of destruction in their wake. Hurricanes are a fact of life for millions of people living in coastal areas. They are particularly common in regions like the Atlantic Ocean and the Eastern Pacific Ocean. These storms are known by different names around the world, hurricanes, typhoons, or cyclones, but their impact is universally devastating. From the Caribbean islands to the southeastern United States, from Southeast Asia to Australia, these storms bring with them the threat of high winds, torrential rainfall, and catastrophic storm surges. But how do these monstrous storms form? What are the ingredients that come together to create such powerful forces of nature? The answer lies in a delicate balance of atmospheric conditions, a confluence of factors that transform a seemingly innocent disturbance into a raging tempest. Understanding these conditions is the first step towards comprehending the awesome power of hurricanes and the importance of respecting their potential for destruction. In the next section, we'll delve into the specific conditions that give birth to these powerful storms, exploring the unique combination of factors that transform a disturbance over warm ocean waters into a swirling vortex of wind and rain. Hurricanes are not random events that pop up anywhere in the world. They have specific breeding grounds, areas where the conditions are just right for their formation. These areas are typically over warm ocean waters near the equator, but not directly on it. Think of a warm bath. The water evaporates, creating warm, moist air. This is similar to what happens in the areas where hurricanes form. The tropics, those sun-drenched regions straddling the equator, provide the ideal conditions for these storms to develop. The warm ocean waters act as a massive heat engine, providing the energy that fuels the hurricane's growth. But it's not just about warm water, it's about the temperature difference between the ocean surface and the upper atmosphere. This difference creates instability in the atmosphere, much like a pot of boiling water, with bubbles of warm air rising rapidly upwards. These rising bubbles of warm, moist air are the building blocks of thunderstorms. The very same thunderstorms that, under the right conditions, can cluster together and organize into a hurricane. The tropics, with their consistently warm ocean temperatures and unstable atmosphere, provide the perfect environment for these storms to develop and intensify. However, warm water alone is not enough to create a hurricane. Other crucial ingredients are needed. In the next section, we will delve into the specific atmospheric conditions that must be present for a hurricane to form, exploring the delicate balance of factors that transform a tropical disturbance into a swirling vortex of wind and rain. Imagine a cake. You can't just mix flour and sugar and expect a delicious treat. Similarly, forming a hurricane requires more than just warm ocean water. You need warm, moist air, low air pressure, and low wind shear. Warm, moist air acts as the fuel. As it rises and cools, moisture condenses, forming clouds and releasing heat. This heat warms the air, causing it to rise faster, creating a powerful updraft. Low air pressure at the surface acts like a vacuum, drawing in more air. Low wind shear is crucial. Too much can disrupt the storm. Imagine building a house of cards in a wind tunnel. Strong winds would make it impossible. When these ingredients come together, a hurricane can form. The Coriolis effect gives hurricanes their characteristic spin. Section 4. The spin cycle, the Coriolis effect, and hurricane rotation. Now let's talk about the spin, the whirling dance that makes hurricanes so mesmerizing and destructive. This spin is not random, it's a direct result of the Earth's rotation, a phenomenon known as the Coriolis effect. Imagine rolling a marble on a spinning merry-go-round. Instead of traveling in a straight line, the marble will curve, appearing to be deflected by an unseen force. This apparent deflection is the Coriolis effect in action. On a rotating Earth, locations at the equator are moving faster than locations at higher latitudes. As air rushes towards the low-pressure center of a developing hurricane, it gets deflected by the Coriolis effect. In the northern hemisphere, this deflection is to the right, causing the air to spin counterclockwise. In the southern hemisphere, the deflection is to the left, resulting in a clockwise spin. This spinning motion, combined with the converging air at the surface, gives hurricanes their characteristic spiral structure, with bands of thunderstorms spiraling inwards towards the calm center, known as the eye. The Coriolis effect is not just a scientific curiosity, it plays a crucial role in shaping the weather patterns we experience on Earth. It's the reason why hurricanes spin, and it also influences the direction of large-scale wind patterns, ocean currents, and even the flight paths of long-range airplanes. In the next section, we'll explore another crucial element in hurricane formation, the role of thunderstorms. These towering clouds are not just a sideshow, they are the building blocks of hurricanes, providing the energy and moisture that fuel these powerful storms. Section 5. Clouds of Chaos. The role of thunderstorms. Hurricanes are not just giant whirlpools of wind, they are complex weather systems fueled by the energy released by thunderstorms. These thunderstorms, specifically a type known as cumulonimbus clouds, are the building blocks of hurricanes, providing the heat and moisture that drive these powerful storms. Imagine a pot of boiling water. The heat source at the bottom causes the water to evaporate, creating bubbles of steam that rise rapidly to the surface. Similarly, the warm ocean water provides the heat source for hurricane formation, causing the air above to become hot and humid. This warm, moist air rises rapidly, cooling and condensing to form towering cumulonimbus clouds. As the warm, moist air rises within these clouds, it cools and condenses, releasing even more heat. This process, known as latent heat release, is a key driver of hurricane intensification. It's like adding fuel to a fire. The more heat that's released, the stronger the updrafts become, drawing in even more warm, moist air from the ocean surface. These thunderstorms don't just provide heat, they also act as giant water pumps, transporting vast amounts of water vapor high into the atmosphere. This water vapor eventually condenses and falls as rain, contributing to the torrential rainfall associated with hurricanes. In fact, some of the most devastating flooding from hurricanes is caused not by storm surge, but by the sheer volume of rainfall. In the next section, we'll explore how scientists categorize hurricanes based on their wind speed, using a system known as the Saffir-Simpson Hurricane Wind Scale. Section 6. Categorizing the chaos. The Saffir-Simpson Hurricane Wind Scale. Just like we categorize earthquakes by their magnitude and tornadoes by their wind speed, we categorize hurricanes based on their intensity. The Saffir-Simpson Hurricane Wind Scale is a 5-category system that classifies hurricanes based on their sustained wind speed and the potential damage they can inflict. Think of it as a ranking system for hurricanes, with Category 1 being the weakest and Category 5 being the most intense. This scale is not just about numbers, it's about understanding the potential impact of these storms. Each category comes with a description of the type of damage expected, ranging from minor damage to complete devastation. This information is crucial for emergency managers, government officials, and the public, as it helps them prepare for the potential impacts of a hurricane and make informed decisions about evacuations and other safety measures. Category 1 hurricanes with wind speeds of 74 to 95 miles per hour can damage roofs, siding, and trees. Category 2 hurricanes with wind speeds of 96 to 110 miles per hour can cause more extensive damage to homes and businesses, as well as uproot trees and down power lines. Category 3, 4, and 5 hurricanes are considered major hurricanes, capable of causing catastrophic damage. The Saffir-Simpson Hurricane Wind Scale is a vital tool for understanding the potential impact of hurricanes. It's important to remember that this scale is based solely on wind speed and doesn't take into account other hazards associated with hurricanes, such as storm surge, rainfall, and tornadoes. In the next section, we'll delve into some real-world examples of hurricanes, highlighting the devastation they can cause and the importance of heeding hurricane warnings. Section 7. When hurricanes strike, real-world examples of devastation. The destructive power of hurricanes is a stark reality for millions of people around the world. One such example is Hurricane Katrina, which slammed into the Gulf Coast in 2005, causing widespread damage and loss of life. Katrina, a Category 5 hurricane at its peak, made landfall as a Category 3 storm, bringing a catastrophic storm surge that inundated New Orleans. The images of flooded streets, submerged homes, and displaced residents remain etched in memory. Another example is Hurricane Andrew, which devastated South Florida in 1992. Andrew, a powerful Category 5 hurricane, caused billions in damage, leveling neighborhoods. These examples highlight the importance of hurricane preparedness and taking these storms seriously. Hurricane Sandy in 2012 caused widespread flooding and damage, showing all hurricanes pose a threat. Next, we'll focus on hurricane preparedness, outlining steps to protect yourself and your property.